So today we are going to start with Taylor's theorem. Before going to the exact statement of the theorem, let's try to motivate you. Suppose I have given a polynomial, I will write it as fx. Since it's a polynomial, I can write it as a0 plus a1x plus a2x square and so on up to an x to the power n. So this is a degree n polynomial. I also assume that all the coefficients of this polynomial, that is ai's, they are all real numbers. So ai belongs to R for 0 less or equals to I less or equals to n. Now since we know that any polynomial is differentiable as many times as you want, the function f is differentiable as many times as I want. And I can see clearly that if I look at derivatives of the function of power bigger than n, then the derivatives will certainly be 0. But now let's notice something. What is f of 0? I can see very clearly that f of 0 is a0. Then what is f prime at 0? So for that I need to calculate what is f prime of x, and I get that this is a1 plus twice a2x plus, that is, terms containing higher powers of x. This then implies that f prime at 0 is equals to a1. Similarly, I can see that f double prime x, which certainly exists, this is twice a2 plus terms containing x. This would then imply that f double prime of 0 is twice a2, which then implies that a2 is f double prime 0 divided by 2. If I go on likewise, I can actually produce the following formula. We can prove that an, or I would say ak, that is fk0 divided by factorial k for all k satisfying 0 less or equals to k less or equals to n. Here the convention is that the 0th derivative means just the function. That means I am not differentiating. So in the light of this, I can actually write down fx as this. This is equals to f0 plus x f prime 0 plus x square by factorial 2 f double prime 0 plus x to the power k divided by factorial k times fk0, and then we go towards the last term. Since it's a degree n polynomial, I have to stop after the nth derivative, because after that all the derivatives are 0. I get x to the power n by factorial n times fn0. Now here what exactly I am using about the polynomials? It seems from this expression all I am using is that the function is differentiable as many times as I want. So given a function, let us say f is a function on a closed interval ab to R. Assume that f is n times differentiable. And then I want to see whether f can be written as an expression like the above which I have written here. So I am looking for a generalization of this for arbitrary function f, which has as many derivatives as I want. Now, in terms of b and a, it should then look like that f of b equals to f of a plus b minus a into f prime a plus b minus a whole square divided by factorial 2 f double prime a plus I get the last term, that is b minus a whole to the power n by factorial n fn a. Question is this true? Notice that this is related to the previous equation. Just put b equals to x and a equals to 0 and get the previous expression. Now we are asking for that given a, if I take any b, then is it true that fb is given as the previous expression? Now if you look at this expression which I have written here, if you fix a, for a fixed, if I call this above expression as star, then star is a polynomial in B, right? That is obvious. That if I fix my A as the base point and keep on varying B, and I look at the right hand side star, that means it is a polynomial in B. But given a function which is differentiable as many times as I want, why it should be a polynomial? For example, you know examples of some such functions: e to the power x, sine x, cosine x. These are not polynomial functions. That means this star cannot be true in general. For polynomials it might be true, but for general functions it's not expected that it will be true. So what exactly is true is given by Taylor's theorem. So now we go to the precise statement of Taylor's theorem. You will see it's very close to the expression which I have written in the box in the red, that is this one. Okay, so let's go to the precise statement of Taylor's theorem. Let f be a function defined on the closed interval ab to R. Suppose f prime, f double prime, and so on up to f n minus 1, which means the n minus 1th derivative of f, are continuous in the closed interval ab, and fn exists in the open interval ab. Then Taylor's theorem says then there exists C such that A less C less B such that f of B equals to f of A plus B minus A into f prime A plus B minus A whole square divided by factorial 2 f double prime A plus so on up to B minus A to the power n minus 1 by n minus 1 factorial times fn minus 1 into a plus the last term, which is b minus a to the power n minus 1 by n minus 1 factorial, but now fn at c. So everywhere it is the derivatives of f at a appearing, but the last term where you get c, and this c now depends on b. If this c is independent of b, then you can see that f will actually be a polynomial, but that may not be the case. That's why the c which I have written in the last term, it depends on the point b. It is exactly like the phenomena in the mean value theorem. The same thing happens in the mean value theorem also. The point c you get, which lies between a and b, that point depends on the endpoints. Here also the point c actually depends on the endpoints. That means that f not actually a polynomial. Okay, it has just this expression. Now let's try to prove this. Well, the proof goes like this. First, I am going to define a function capital F, but the function f will depend on n. So I define capital F at n minus 1 at x. The idea is you keep b, put x instead of a in the above expression. That is, capital F of n minus n into x is f of b minus f of x minus b minus x into f prime at x minus b minus x whole square divided by factorial 2 f double prime x and so on up to b minus x to the power n minus 1 by n minus 1 factorial into f n minus 1 into x. That means, what is our aim? I essentially have to prove that there exist C such that A less C less B, and if n minus 1 into A equals to B minus A to the power n by factorial n times fnc. This is what I need to prove. Now what I do is I vary the parameter n. So for k lesser equals to n minus 1, what I do is I define a function fk analogously as the previous one. I define fk at x equals to fb minus fx minus b minus x into f prime x and so on up to my last term is b minus x to the power k by factorial k into fkx. Okay. Among this class of functions, f n minus 1, I have already told you what it is. Now first thing I claim is, so this is my claim, the claim is that fk prime at x is equals to minus b minus x to the power k by factorial k times fk plus 1x. To prove this, we can actually proceed inductively. So let us first take k to be equals to 1. So what is then f1x? f1x is just fb minus fx so f1x is just fb minus fx minus b minus x into f prime x, and then f1 prime at x turns out to be minus f prime x minus b times f double prime x plus f prime x plus x f double prime x. If I cancel terms, what I get is minus b minus x times f double prime x. This precisely matches with the formula, with the claim which I have written for k to be equals to 1. Now what I am going to do is I will just assume this result and try to prove it for fk plus 1. Okay. So assume that the claim is true for k let us see the formula for fkx. It is b minus x to the power same power k, then factorial k, then derivative has one power extra, that is k plus 1. So when we write down fk plus 1x, it should go to up to k plus 2. From the given formulas, it is very clear that fk plus 1x is actually fkx minus b minus x to the power k plus 1 divided by k plus 1 factorial into fk plus 1x. Now I look at the derivative of this. I look at fk plus 1 prime x. What I get is fk prime x. Now the derivative of the next term, which I can calculate surely, which is plus b minus x to the power k by factorial k into fk plus 1x minus b minus x to the power k plus 1 divided by k plus 1 factorial into fk plus 2x. Now I plug in the formula for fk prime x, which I have assumed. So this then is minus b minus x to the power k by factorial k into fk plus 1x. That is my assumption. Then I just write down the other terms, which is b minus x power k by factorial k into fk plus 1x, then minus the other term, that is b minus x to the power k plus 1 by k plus 1 factorial into fk plus 2x. Now I can cancel the first two terms, that is this one and this one. So the answer is the third term, but that is precisely same with my claim. So we have proved the claim for all k's. So in particular, this implies the result is true for if n minus 1 also. So if n minus 1 prime x now turns out to be minus b minus x whole to the power n by factorial n, then fn x. Okay. Now I am going to use this in the following form. What I do is I define a function g on closed interval ab by gx equals to f n minus 1 x minus b minus x to the power n divided by b minus a to the power n into f n minus 1 into a. Now clearly g is a differentiable function. And then we check certain things here, that what is g of b, that is fn minus 1b, because the other term is 0, b minus b, which is 0. So I just get fn minus 1b. But now let us look at the formula for fn minus 1b. Fn minus 1b, the written formula, if I put x to be equals to b, I can certainly see from this formula that fn minus 1b is 0. So this is equals to 0. What is g of a? That is fn minus 1a minus b minus a power n divided by b minus a power n into fn minus 1a, which is same as 0. So g is a differentiable function which vanishes at the endpoints. So this implies, by Rolle's theorem, there exists C in the open interval AB such that g prime of C is equals to 0. Now g prime of C equals to 0 implies fn minus 1 prime at C minus the derivative of the other function at C. That means n times b minus c to the power n minus 1, the sign would be plus, divided by b minus a power n fn minus 1 into a, that is equals to 0. But remember, I have an expression for the function capital Fn minus 1 prime, which I am going to use now. This would then imply that minus b minus c whole to the power n by n minus 1 factorial into fn c. This follows from my claim, which I have proved, then plus the term which I have calculated, b minus c to the power n minus 1 divided by b minus a whole to the power n times fn minus 1a, which is equals to 0. This would then imply that fn minus 1a, remember the way I have defined the function capital Fn minus 1, my job was to show that capital Fn minus 1 at a is actually the last term in the Taylor series, that is the term involving c, which we will see how it comes out. This is then equals to b minus a power n divided by n into b minus c power n minus 1 into b minus c power n divided by n minus 1 factorial into fn c. If I calculate this, what comes out is b minus a power n divided by factorial n into fn c, which is precisely I wanted to prove. Now I just write down the definition of fn minus 1 at a, which is equals to the last term of the Taylor series. That proves Taylor's theorem. Now we address another issue. It is the convergence problem. Suppose I have a function f such that all the derivatives of f exist of all possible order, that is f prime, f double prime, so on, fn, and it goes on. So for example, I can take fx to be equals to e to the power x. It's a function whose derivatives of all order exist. I could have also taken fx equals to sin x, for which also derivatives of all order exist. So I look at some such function, and then I can certainly write down this f0 plus x f prime 0 plus x square by factorial 2 f double prime 0, and I go on writing it. Notice that I can go on writing it because derivatives of all possible order exist, and hence this series makes sense. So I actually have an infinite series at my hand. I look at this summation n from 0 to infinity fn 0 by factorial n times x to the power n, with the convention, of course, with the convention that f0 is f. So I get an infinite series, or if you recall, I actually get a power series. This is called the Taylor series of f. But the question now is whether this series makes sense. Does this series converge? Because it's an infinite series. And if it does it converge to the function f? Well, it turns out that in many cases it does converge to the function, but there are examples of functions for which the Taylor series, even if it converges, it may not converge to the function. So we'll see all these examples. But before that, let's first try to understand how exactly we determine whether the Taylor series converges to the function or not. So for that, I am going to use Taylor's theorem. What I have proved is that given x, there exists C which lies between 0 and x, such that fx is equals to f of 0 plus x f prime 0 plus x to the power n minus 1 by n minus 1 factorial f n minus 1 0 plus x to the power n by factorial n times fn c. Now writing in different fashion, I will say that this implies that x to the power n by factorial n into fn c is equals to fx minus summation k equals to 0 to n minus 1 x to the power k by factorial k into fk0. Notice that the term written in the sum is precisely the nth partial sum of the Taylor series. And if I want to know if whether the Taylor series converges to the function or not, all I have to check is that the modulus of fx minus the partial sums go to 0 as n increases, which is same as saying that the left hand side should go to 0 as n goes to infinity. So we call that the remainder term. So I define Rn fx to be equals to x to the power n by factorial n times fn c. Notice here that c do depend on x. So for the convergence of the Taylor series, what we have to look at is mod Rn fx, which is same as modulus of fx minus summation k from 0 to n minus 1 x to the power k by factorial k times fk0 should go to 0 as n goes to infinity. This is required for convergence of the Taylor series to the function. Well, there are certain easy cases where this happens. So I will just write it here. Assume that Fn, that is the nth derivative of f, is bounded by a number m for all n. That is, I am saying that modulus of fnx is lesser equals to m for all n and x. If this happens, well, as example, let us first see the function fx equals to e to the power x. But first we have to be sure that if this boundedness of the derivative is there, then I will get the convergence. Why do this happens? Because then modulus of Rn fx I look at. What is its definition? I know it is modulus of x to the power n by factorial n times fnc. Since fnc is bounded by m, this would mean that this is lesser equals to m times x to the power n by factorial n. Now I will just guarantee that x to the power n by factorial n converges to 0 as n goes to infinity. Well, for that what do we do is I define yn equals to x to the power n by factorial n, and then I note that yn plus 1 divided by yn, it turns out to be x to the power n plus 1 by n plus 1 factorial into factorial n divided by x to the power n, which is x by n plus 1, but my x is fixed, so it converges to 0. And then by a previous exercise which we have dealt with while dealing with sequences, that this implies the actual sequence yn converges to 0. That means Rn fx converges to 0. That means the nth partial sum converges to fx for a given x. Now I am going to use this for the function fx equals to e to the power x. Let us see what happens. I have then f prime at x is e to the power x. Not only that, for any arbitrary n, fn x is e to the power x. This then implies that fn0 is equals to 1. Then what is my Rn fx? This is then x to the power n by factorial n into fnc, that is x to the power n by factorial n into e to the power c. And this is certainly equals to fx, which is e to the power x, minus summation k from 0 to n minus 1 x to the power k by factorial k into fk at 0, which I have noticed is actually equals to 1. Now I have given a fixed x. If x lies between minus m and m, let us say, then e to the power c is bounded by e to the power m for all x in minus m m. This then implies that mod Rn fx is lesser equals to mod x to the power n divided by factorial n into e to the power m. कैसेट खत्म हो गया. So I get that Rn fx is less or equals to mod x power n divided by factorial n into e to the power m. Now in e to the power m there is no n dependence. N dependence is only on mod x and factorial n. But I have already established that the first factor, this goes to 0 as n goes to infinity, and e to the power m is a constant. So this goes to 0 as n goes to infinity. This then implies the familiar formula that e to the power x is actually 1 plus x square by factorial 2 plus x to the power n by factorial n and so on. This series converges to e to the power x for all x, and the right hand side is precisely the Taylor series of the function. Now let us look at example of another familiar function. I take fx to be equals to sin x. This is a good example to deal with, you will see, because whatever derivative of fx I look at, it is either sine or cosine. In any case, they are all bounded functions. So the convergence of the Taylor series won't be much of a problem. And since I want to write down the Taylor series of the function around 0, it will turn out that the derivatives, precise value of the derivative I can calculate because it is either sine or cosine. Well, a calculation yields that fn at 0 is equals to minus 1 to the power k if n is of the form 2k plus 1, and it is equals to 0 if n is equals to 2k. That means the even powers of x which should appear in the Taylor series will disappear because the derivative at 0 will be 0. So the powers of x which will appear in the Taylor series of sine functions are certainly going to be the odd powers. Well, this actually reflects the fact that sine of minus x is minus of sine x. That property is taken care of by these odd powers. Well, then we will try to write down the Taylor series of the function. It will then turn out to be summation k from 0 to infinity x to the power k by factorial k into fk0. I can say that this is equals to fx as all possible derivatives are bounded by a single constant. All derivatives are bounded by 1. This then implies that sine of x is summation k from 0 to infinity minus 1 to the power k by 2k plus 1 factorial into x to the power 2k plus 1. Using the same technique, now you can write down the Taylor series of the function fx equals to cosine x also, because again I can calculate all the derivatives at 0. Similarly, all possible derivatives are bounded by 1, so the Taylor series will certainly converge, and if you calculate the derivatives, you will see at 0 only the even terms survive, and hence you get the Taylor series of the cosine function, which you probably already know as the series for cosine x. But that series represents sine x or cosine x actually follows from the Taylor's theorem, and since the Taylor series converges, the function is given by that same series. So far so good. Now we will look at an example where the Taylor series converges but it does not converge to the function given. That can also happen. Now, to construct an example of a function for which the Taylor series does not converge to the function, the basic idea is to construct a function which has derivatives of all orders. That has to be there, otherwise I cannot write down the Taylor series, but manage a function such that all its derivatives at the point 0, let us say, is 0. Suppose that happens, then what will happen? So this is my example 3. Try to construct a function f such that fn at 0 is 0 for all n. Suppose I do this, then the Taylor series converges to the function would mean that fx equals to summation n from 0 to infinity fn 0 by factorial n into x to the power n. But I know that fn 0 is 0. That means the right hand side is actually equals to 0. So all I have to do is I have to construct a function which is non-zero and all whose derivatives at 0 is 0. If that happens, then the Taylor series of the function cannot converge to the function. So the question is whether some such functions exist. Well, they do. This is how we construct them. I define the function fx equals to e to the power minus 1 by x if x is bigger than 0. I define it to be equal to 0 if x equals to 0. Notice that one thing is very clear here, that the function is continuous. Well, I just have to check that limit x going to 0, fx is 0. That means limit x going to 0, e to the power minus 1 by x is equals to 0. If I put 1 by x equals to t, this would mean limit t going to infinity e to the power minus t, which is same as limit t going to infinity 1 by e to the power t, which is less or equals to limit t going to infinity 1 by t. This is simply because e to the power t is bigger than or equals to t. That follows from the Taylor series as t is positive, which is equals to 0. So the function is continuous. So question is the function differentiable at 0? Obviously, the function is differentiable if x is less than 0, and since the function is 0 on the negative axis of the real line, you can also see that the derivative also has to be equals to 0. Now if x is bigger than 0, e to the power minus 1 by x is certainly a differentiable function. So 0 is the only point where we have to check the differentiability. So let us check it at 0 and try to find out what is f prime 0. So f prime 0 by definition is limit h going to 0 fh minus f0, but f0 is 0, so it is fh by h, that is limit h going to 0 e to the power minus 1 by h divided by h. I again play the same trick of putting 1 by h equals to t. I will then get limit t going to infinity. Well, here I am bothered about h going to 0 plus, let me say that. What I get is t times e to the power minus t. This is then limit t going to infinity, t divided by e to the power t, which then is less or equals to limit t going to infinity t by t square. Because e to the power t is bigger than or equals to t square by t square by 2. So what I get here is limit t going to infinity 2 by t, which is again equal to 0. So the derivative exists, and not only that, the derivative at 0 is 0. So now I want to prove that fn 0 is equals to 0 for all n. This is my claim. I will try to prove it by induction, and for that obviously I need the expressions of fn's if x is bigger than 0. So the another claim is that fnx is equals to e to the power minus 1 by x times a polynomial Pn at 1 by x for x bigger than 0, where it will turn out that Pn is of degree 2n, which is not very important for us right now, but this is what we want to prove. So let us see whether the thing is true for n equals to 1. The first one we have seen that f prime 0 is 0. So what is f prime at x if x is positive? We can just simply differentiate. It is e to the power minus 1 by x times the derivative of minus 1 by x, that is minus of 1 by x square, which is e to the power minus 1 by x into 1 by x square. So I will assume the induction hypothesis that the result is true for n. I want to prove it for n plus 1. So what is f n plus 1 x? That is the derivative of the function e to the power minus 1 by x times Pn x. Now there is a polynomial here which I know, so I will write down the polynomial here. It is k from 0 to 2n ak x to the power k, the prime of this function. This is my fn plus 1x. Well, this then turns out to be e to the power minus 1 by x into summation k from 0 to 2n ak x to the power k times 1 by x square plus e to the power minus 1 by x times the derivative, so that is k from 1 to 2n. So fn plus 1x is e to the power minus x times the polynomial at 1 by x. So I have the power minus here, and then I differentiate. What I get is from k equals to 1 to with a minus sign ak divided by x to the power k plus 1 times k. This is what I get. Now if I add the polynomial terms, I see that I get a polynomial of degree 2 times n plus 1. So this is e to the power minus 1 by x times summation k from 0 to 2n ak by x to the power k plus 2 minus k from 1 to 2n k ak by x to the power k plus 1. You see, I get a polynomial whose degree is 2 times n plus 1 and in the variable 1 by x. So I get e to the power minus 1 by x times a polynomial p at the point 1 by x. So this verifies my second claim. But what about if n plus 1 0 then? That I have to calculate. So this is then limit h going to 0 fn h minus fn 0 divided by h. Since the function is 0 on the negative axis, all these fn h's are anyway 0. So h going to 0 minus, if I take, I am certainly going to get 0. So what I am bothered about is h going to 0 plus. Now I have an expression for fn h that I will put it is limit h going to 0 plus, I know the expression of f and h, it is e to the power minus 1 by h times a polynomial p at 1 by h, then I have another 1 by h here. Now if I write down the explicit expression of the polynomials and term by term, then I can look at the limit. So I am essentially bothered about finding the limit h going to 0 plus e to the power minus 1 by h times 1 by h to the power some m. M is bigger than or equal to 0 certainly. Now to calculate this limit, I again use the same trick which I have used. It is limit t going to 0, it is limit t going to infinity, t to the power m e to the power minus t. Now this is then lesser equals to limit t going to infinity, t to the power m into m plus 1 factorial divided by t to the power m plus 1, as e to the power t for t positive is bigger than or equal to t to the power m plus 1 divided by factorial m plus 1. Now this certainly goes to 0 as t goes to infinity. So this implies that all the derivatives at 0 is 0, and hence the Taylor series of this function, if I look at, the Taylor series turns out to be 0. So it cannot converge to the function because the function e to the power minus 1 by x is always non-zero if x is positive. So how can it happen that the Taylor series of the function converges to the function for all x? That is not true. It can converge to the function if x is negative, but for positive x it cannot converge to the function. So here we see example of a function for which the Taylor series although converges because it is 0 for all x, but it does not converge to the function.